Have you ever been sitting at the kitchen table, looked at your reflection in a spoon, and just thought, what is going on here? Well, it turns out there's some seriously cool science hiding in your cutlery drawer. Today, we're going to use this simple, everyday object to unlock some of the biggest secrets of light and mirrors. All right, let's get into it. So, this is the core question, right? You look into the bowl of the spoon, the part that holds your cereal, and you're upside down. But then you flip it over to the shiny back, and suddenly you're right side up again, but all stretched out and wide. It's like a pocket-sized funhouse mirror. So how in the world does one object pull off two totally different reflections? You see, the answer starts with something super basic. The only reason you can see, well, anything, your phone, your friend across the table, or a spoon, is because light bounces off that thing and travels into your eyes. Without reflected light, everything would just be dark. And that bouncing action, that's what we call reflection. Now, light doesn't just bounce around all chaotic-like. No. It follows a very strict but super simple rule, the law of reflection. Just imagine throwing a tennis ball straight at a wall. It comes straight back, right? But if you throw it at an angle, it bounces off at the exact same angle. Light does the exact same thing every single time. This one law is the key to everything. So if the rule is so simple, why is a spoon so, well, weird compared to your bathroom mirror? A flat mirror is totally predictable. Your reflection is upright, it's the same size you are, you know the drill. But a spoon, it throws all those expectations out the window. And here's the kicker. It's not breaking the law of reflection. It's following the exact same law, but just applying it to a curved surface instead of a flat one. And here is the first major clue to solving our mystery. When you pick up a spoon, you're not just looking at one type of mirror. You're actually holding two. That's right. The inside surface and the outside surface are fundamentally different, and they bend light in totally opposite ways. Let's give these guys their proper scientific names. The inside of the spoon, the part that curves inward like a cave, that's a concave mirror. The back of the spoon, the part that bulges out towards you, is a convex mirror. You can see right here what those two shapes look like. Concave and convex. Okay, so to really crack the code on why one side flips you upside down and the other doesn't, we need to learn a few key terms. Think of this as learning the basic grammar for how any curved mirror works, whether it's a spoon or a giant telescope mirror. This guy here is our master diagram. Think of it as our map. Seriously. All the secrets of that weird spoon reflection are hidden in the relationships between these different points and lines. Let's start with the easiest one on the map, the pole, which you'll see marked with a P. It's literally just the dead center of the mirror surface. It's our main reference point, our starting line for everything else. Next up, we have the center of curvature, or C. Now, this one's a little more mind-bending. I want you to imagine that your spoon is just a tiny little piece that was sliced off of a giant, perfectly round glass ball. The point C is the exact center of that huge imaginary ball. It basically tells us how sharp the mirror's curve is. And hey, if you know where the center of that imaginary sphere is, you can measure its radius, right? So the distance from the center of our mirror, the pole, out to that imaginary center point C is called the radius of curvature. We just call it R. It's a number that measures the curve. Okay, so we've mapped out the physical shape of the mirror. But the most important point for understanding the image it makes, well, it isn't even part of the mirror at all. It's a special spot in space where the mirror does something amazing with light. This spot is called the principal focus. So, how do we find this magical spot? Well, there's a pretty cool little experiment you can do. If you take a concave mirror, remember, that's like the inside of a shiny spoon, and you point it towards the sun to reflect light onto a piece of paper, something really neat happens. As you move the paper closer and farther away, you'll find one perfect spot where all that sunlight gets concentrated into one tiny, incredibly bright dot. That dot, that's the focus. And look, before we go any further, a really, really important warning here, straight from the source material. This experiment works because the mirror is basically a magnifying glass for the sun's energy. So please, never, ever look directly at the sun or at its reflection in a mirror. You can cause serious, permanent damage to your eyes. Okay? Safety first. So this diagram, this shows us exactly what was happening with the paper. Light rays from something far away, like the sun, traveled pretty much parallel to each other. When they hit the curve of the concave mirror, every single one of those rays gets bounced to one single point, the principal focus, marked here as F.
That's why the paper can get hot enough to burn. All that energy is being focused on one tiny spot.
Now watch what happens when we use a convex mirror, the back of the spoon. It does the complete opposite. Instead of gathering light together, it spreads it out. The parallel rays hit the surface and bounce away from each other, or diverge. To our eyes, it looks like all those scattered rays are coming from a single focal point. That's actually behind the mirror. And this brings us to our last key piece of the puzzle. The distance from the center of the mirror, that's the pole, P, to that special focus spot, F, has a name. It's called the focal length, and we write it as a lowercase f. This one number tells you pretty much everything you need to know about a mirror's focusing power. So we've got the physical shape of the mirror, which we measured with its radius of curvature, r. And we've got its light-bending power, which we measured with its focal length, f. You might think those are two separate things, but it turns out they are locked together by a beautifully simple piece of math.
And here it is. R equals 2f. That's it. All that means is that for these mirrors, the radius of curvature is always exactly twice the focal length. So that focus point isn't in some random place. It's always located precisely halfway between the mirror's surface and its center of curvature. It's the simple, elegant formula that's behind all those strange reflections.
All right, let's put it all together. Let's solve the spoon mystery once and for all. The inside of the spoon, the concave side, focuses light rays in front of it. This creates what's called a real image, and that image is upside down. The back of the spoon, the convex side, spreads light out. This creates a virtual image that only appears to exist behind the mirror, and it's always upright. And the weird stretched out look? That's just because the spoon isn't a perfect sphere, but the physics is exactly the same. And just like that, you know the secret of the spoon. But what's so cool is that this isn't just about spoons. That convex mirror on the passenger side of your car, it uses this exact principle to give you a wide, upright view of the road. And the giant concave mirrors inside massive telescopes, they use their focus to gather faint light from galaxies billions of light years away. The physics in your kitchen drawer is the same physics that explores the entire cosmos. What else around you is hiding a scientific secret just like this one?